This is Dr. Anthony Revis, and this is SVSU General Chemistry 111, Chapter 9, Gases. Lecture 1 of Chapter 9 on gases. In this chapter, we will discuss the topic of gas pressure. We will look at the relationship between pressure, volume, the amounts, and temperatures. We will look at the ideal gas law. We will look at how to examine stoichiometry of gas substances, mixtures, and reactions. We will talk about effusion and diffusion of gases. We will look at the kinetic molecular theory. And we will look at non-ideal behavior. All of these topics will be covered, but they might not be covered in this specific order. Let's begin this discussion by talking about pressure. Whether by creation, evolution, or some other act of existence, pressure is part of the environment. It is common to the environment. It is part of our existence in this environment. So pressure is indigenous, if you will, to our environment. In fact, it's such a part of our environment that we rarely exactly feel the pressure, but it's here. Now, that pressure that is part of our environment, part of the Earth's environment, is rated at what we call 1 atmosphere. In fact, we talk about it as atmospheric pressure. It is the pressure within our atmosphere. And that pressure is rated at what we call 1 atm, 1 atmosphere. Okay? And if we could imagine taking a square inch column of air molecules, that would be the pressure exerted against it. And that would be 14.7 pounds of pressure if we rated it in square inches. As we go through this chapter, you will learn other units used to express pressure. So, we now know we have 1 atmosphere, which is equivalent to 14.7 pounds of pressure per square inch. Therefore, we could in fact use that as a conversion factor. Keep in mind that any equality may be used as a conversion factor. So, that's our pressure. 14.7 pounds of pressure per square inch, 1 atmosphere. We like to note that within the troposphere, air is composed of about 78% nitrogen, 21% oxygen, and 1% of other gases, of which carbon dioxide is part of that. There's also some argon, a little bit of carbon monoxide, of course, and then you have these other gases as well. So, our air, the air we breathe, has this composition, and it exists at 1 atmosphere. So, what's happening within the troposphere is happening with 1 atmosphere of pressure exerted against it. If we were to examine the periodic table, we find that there are several gases that exist naturally at room temperature. And when we talk about room temperature, we generally refer to it as 25 degrees C or 298 K. The noble gases naturally exist as gases under these conditions. That's group 18 or 8A. We also have fluorine and chlorine, both exist as gases. Then we have nitrogen and oxygen, which is part of the composition of air. The major part of the air is nitrogen, and it's the diluent for oxygen. So again, this table shows you the gases that exist naturally at 25 degrees C, 298 K. Note that as we have discussions about gases, In general, we will talk about them in K units. For many of the calculations, it will use K. You'll know when degree C might be used. But in general, you want to start to think in K, which means you take degree C plus 273 will give you K. And K is not degrees K, it's just K. So what is gas pressure then? Gas pressure is caused by the force exerted by gas molecules colliding with the surfaces of an object. In other words, the pressure happens because the gas molecules are colliding or running into or bombarding surfaces of objects. Although the force of each collision is very small, any surface of appreciable area experiences a large number of collisions in a short time, which can result in high pressure. In other words, the frequency is so high that it increases the pressure. And when we consider the area factors in thinking about these collisions, we discover that we can build up a fair amount of pressure. That brings us to the equation for pressure, which is pressure equals force divided by area. So pressure and area are inversely proportional. Be aware of that. But pressure is directly proportional to the force. More pressure, higher force. Less pressure, lower force. We also can substitute in, where appropriate, the formula force equals mass times acceleration. So these are the important equations that are related to gas pressure. The units for pressure can be in pascals, which is 1 Newton per meter square. We can have units of 1 atmosphere equals 760 millimeters of mercury, which equals 760 torr. In general, in most CHEM classes, we allow you to directly substitute without proving it that 760 millimeters of mercury equals 760 torr. So if in a problem you see 760 millimeters of mercury and it asks for the answer in torr, more times than not, we allow you to simply exchange those units, cross out the millimeters of mercury, write the word torr, and continue to do the calcs, or vice versa. Okay? Be aware of that. That's a direct swap that is usually permitted in most Gen Chem and freshman chemistry classes. 1 atmosphere, slightly over 100,000 pascals. So those are your units. On the right, we show you a diagram for how this pressure might be acquired. It's based upon the pressure, like capillary pressure, the atmospheric pressure's down on it, and we have 76 centimeter column there that can experience the downward push of the atmospheric pressure, and it rises up inside the capillary. Note that a manometer is one of the devices used to measure pressure. That is a point you want to memorize, that a manometer is used to measure pressure. That's a common device. And a mercury manometer has historically been used for that. Because the units can vary depending on where you are in the world, the SI units for pressure are pascals. Be aware of that. So 1 pascal is defined as the pressure exerted by 0.1 millimeter height film of water on the surface beneath it. Because the actual values can be a long number, kilopascals is often used. A related unit of pressure is bar, and bar is used a lot in analytical instrument labs. That unit is very popular in, for example, HPLC. So 1 bar equals 10 to the 5 pascals. These are conversion factors to be aware of. You can memorize these, or if you happen to forget them, more times than not, we'll give you the conversion factors. I don't require a lot of memorization of conversion factors. There are some basic ones, however, that we just simply expect you to know because you've been a part of the course. So, here's some pressure conversions to be aware of and to have handy. 1.013 bar equals 1 atmosphere equals 760 millimeters of mercury, which is our direct substitution for 760 torr and vice versa, which equals 14.7 psi equals 101.3 kilopascals. So these are some units to be aware of for conversion purposes. Note that the first part of this lecture is really exposing you to the units that we use and exposing you to the language. Once we get through this part, the rest of the lecture will really be at looking at how problems will work using gas laws. Let's talk a little about pressure and temperature relationship. The effect of temperature on gas pressure. What is it? To illustrate the effect, we use this diagram of showing you these hot plates. And we have hot plate on, hot plate medium, hot plate high. And we look at the response by pressure. When the heat is off, it's low pressure. When the heat is medium or warm, it's medium pressure. But when it's high temperature, we get high pressure. So, that means that pressure and temperature are directly proportional. Okay, you got it? So, as temperature goes up, the pressure goes up. And that's the important factor. Pressure goes down, temperature goes down. So be aware of that. As gas is heated, the pressure of the gas inside the sphere increases in our illustration and is a relationship worth noting. For a constant volume and constant amount of air, constant mass, constant moles, the pressure and temperature are directly proportional, provided the temperature is in K. That is important. So if you do a calculation and you discover that it doesn't appear to be that way, it could be that you're using the wrong T. So converting your temps to Kelvin is a very important thing to note when you're doing these calculations. Here we show you a graph and some data to support this. As the gas is heated, the pressure of the gas in the container increases. So it's a linear relationship, directly proportional. Pressure goes up, degrees K goes up. And we show you the values on the left side in the table, and then we show you the graph on the right side. So you want to be aware of this relationship. It is a very important relationship to think about in doing problems and in understanding gas law relationships. Now, before we start to learn how to use each of the gas laws to acquire certain data, I want to introduce you to a concept called standard temperature and pressure. I want to do that now because I want to use that in some of the problems we're going to work. Some textbook will introduce this concept after the gas laws have been introduced. I prefer to introduce it now so that I can use it and talk about it as I go through the gas laws. So ready? Here we go. Let's talk about this concept of molar volume and STP. Even though we've not told you exactly how to acquire these moles and these grams, you by now understand that reactions take place at a molar level, involve their moles, involve the collision of molecules. Those molecule collisions are happening based upon molar relationships. All right? So let's talk about molar volume and standard temperature and pressure. Exactly what it says. There's a standard temperature and there's a standard pressure. And we're going to tell you what those are. And we're going to tell you what it means to be at STP. STP is a very important concept in understanding the principles of gas laws. So here we go. When a gas is at STP, standard temperature and pressure, it's at those conditions, and those conditions are 0 degrees C, which means 273 K, and 1 atmosphere, which is 760 millimeters of mercury, or 760 torr, or 14.7 pounds per square inch, which we don't use in the SI system. But that's what standard temperature and pressure is. Those are the values for standard temperature and pressure. Okay? So, when a gas is at STP, its molar volume can be written as a conversion factor and used to convert between moles of a gas and volume in liters. In other words, we meter in gases. Gases don't go on an analytical balancer. We pump them in from a tank. So as we pump them in from a tank, we use volume to decide how many moles of that gas we have. And from the moles of the gas we have, we can calculate the grams we have. You get it? So it's very important that we understand that particular concept. That volume is a very important variable, is a very important unit in carrying out these calculations and acquiring data for gas law type problems. So oftentimes we will use STP, standard temperature and pressure, just to get at a volume that we can convert to moles and vice versa. All right? So that's why molar volume by STP is so important. We don't typically weigh the gases. You can, in fact, but you have to meter it into a tank, and that tank would have to be weighed. But more times than not, we meter it by volume, and we can do the conversions. Now it's actually done all by app. But because you're taking this class, you have to learn to do it by hand. Okay? Now, the volume of gases can be compared at STP when they have the same number of moles of gas. And that's very important, and you're going to see how to do that. The volumes of gases can be compared at STP when they have the same number of moles of a gas. Okay? Again, note that standard temperature is exactly 0 C, which is 273 K. Standard pressure is exactly 1 atmosphere. And because of that, we have discovered, or we now know, that 1 mole of a gas equals 22.4 liters at STP. I just talked for approximately 2 minutes to tell you that very basic principle. End of the day, that's the bottom line. You need to know that 1 mole of any gas equals 22.4 liters. That is the bottom line. It doesn't matter what the gas is. At STP, 1 mole equals 22.4 liters. The nature of the gas does not matter. 1 mole at 0 C and 1 atmosphere is exactly 22.4 liters. Okay? We show that to you here on this concept slide. 1 mole of any gas at STP contains 22.4 liters. Again, standard T is 0 C or 273 K. Standard P is 1 atmosphere or 760 millimeters of mercury or 760 torr. So if you have helium, 1 mole of helium is 4 grams. At STP, it has a volume of 22.4 liters in that balloon. If you take ammonia, 1 mole of ammonia is 17 grams. It has exactly 22.4 liters inside that balloon. If we take 1 mole of oxygen, which is 32 grams of oxygen, it has exactly 22.4 liters inside that balloon. That is the take-home principle of STP. So, if in a problem it says, I have a balloon at STP, right away note, you know your volume. The volume is 22.4. Doesn't matter what the gas is. It said I have a gas of X at STP. Right away, write on your paper, 22.4 liters. That's the volume. It doesn't matter what the gas is. Doesn't matter where the gas came from, how it was produced. If it's at STP, that means 22.4 liters. And we're going to use that principle to work some problems in this lecture and in lectures to come, and certainly in homework problems. Okay? Be aware of that. That's an important principle. You can take that then and use it as a conversion factor to carry out calculations. Let's do one. What is the volume in liters of 64.0 grams of oxygen gas at STP? Right away, as soon as we said that, we know that at STP, 1 mole equals 22.4 liters. So we have 22.4 liters in every 1 mole. So we can do a conversion factor, a dimensional analysis conversion, to determine how many liters we have in this quantity, 64.0. So we start with our given. You always start at your given. You do a cross hash bar down to grams because dimensional analysis tells you to follow the cross out math. And since we had grams in this given, we need grams in the bottom. So now we take grams up to mole, and then we convert it across the liters by using the 22.4 liter per 1 mole because we know that is a conversion factor, and we know that is an allowed relationship or ratio in gas law chemistry. So when we set up these equations with the conversion to mole first, and then the conversion to liter first, shown on this slide in brown color for the conversion to liter, we obtain 44.8 liters of oxygen. And you intuitively knew that, right? Because you knew that 1 mole of oxygen was 32 grams. And therefore, since we have 64, we know that we simply double it. However, you must show that through the proper math calculations. In other words, you can't set up a logical equation or a logical statement and say, therefore, it is this. You must show it mathematically as we show it here. So this is how we use the 22.4 liter per mole or 1 mole per liter. Use it as a conversion factor when we need to get to liter and we're at STP. We need volume and we're at STP. We use this conversion factor. And I wanted to introduce that concept up front so we can talk about it as we work through the other gas laws. So what are all these gas law relationships we've been mentioning? This slide summarizes the important gas laws that you will see. You will also see the ideal gas law, and you will also learn about diffusion and effusion. So we summarize them here. We will go through each of these individually in the slides to come. Note that these formulas take advantage of being able to rearrange equations. They also take advantage of knowing when the gas is at constant temperature, moles, pressure, moles, volume, moles. When that is the case, we mathematically cancel out that particular variable using the rules of math, which leads us to the primary relationship, which is actually the formulas we use. So the actual formulas we use are shown on this slide in the column labeled as relationship. The equation to the far left is the combined gas law. And in fact, for some mathematically minded students, they will simply remember the combined gas law, and by the rules of math, they'll know if it says constant temp, I simply eliminate it. They'll know that if it says constant pressure, they eliminate it, or they'll know if it's constant volume, it will be eliminated. So it's up to you how you memorize these, but they're straightforward formulas, and it is possible that these will also be given to you, but we encourage you to really memorize them in case we don't give them to you on any exam. In some CHEM courses, the formulas are given. We also have Avogadros Law, which is derived when there's constant pressure and constant temperature. And the relationship is shown here in the volume per mole of 1 to the volume per mole of 2. We show you these again at the bottom slide here. Again, we're showing it to you in several different forms just to familiarize you with the type of math that you'll see. It's fairly straightforward math. And when the problems are being worked, make a note of the following. You'll always know which formula to use by simply marking up your problem with the variables as they're mentioned. Okay? So if it gives you temperature, mark a T. If it tells you pressure, mark a P. If it gives you moles or grams, you mark it. If you ever have grams, think moles. And if you label these directly on your problems, you'll be able to see which formula you're using. So we can't trick you here. Simply look at the variables in the problem, in the question, and it'll tell you which equations you're using. Typically, you'll have 3 of the variables listed and you'll be looking for the 4th. Now that we've introduced the concepts, we've exposed you to the units, we've talked about STP, and you've started to look at the variables involved in gas law equations and gas law chemistry. Let's talk more specifically about these individual gas laws. And these gas laws are named after famous scientists who did most of the research on the topic. The first one is Boyles Law. Boyles Law states that the pressure of a gas is inversely proportional or inversely related to its volume when T and N are constant. When it says when T or N are constant, don't panic. That simply means they are not in your equation. So in reading the problems, when it says something is constant, that simply means ignore it. Do not write an equation that contains those variables. Okay? So T and N are constant. That means in my equation, I won't see T and N. If the pressure increases, then the volume decreases. That brings us to a basic equation of P1V1 equals P2V2. Again, that means then that if the pressure increases, then the volume decreases. And that is a principle that you will want to retain. We show you examples in the drawing at the right side where you have V1 equals 4 liters, P1 equals 1 atmosphere, then P2 would equal 2 liters, therefore P2 would be 2 atmosphere. So you see the relationship there, okay? And that's important. You exert more pressure, that means the volume is going to go down, okay? Exerting more pressure means pressure increase, which means volume decrease. We show you the curves on the left side. Essentially, when you see these curves, and oftentimes in Gen Chem, we'll show you a curve and ask you which law does it fit. If it involves pressure and volume, then it's Boyles Law. Regardless of which format it's in, look at the X and Y coordinates, and if they have pressure and volume, then it's Boyles Law. That's it. Boyles Law involves pressure and volume. That is a point you will want to retain. Boyles Law, pressure, volume, which means T and N are constant. So let's work a problem using Boyles Law. Here it is. When Whitney, or Sarah, or Bobby, or Randy, had an asthma attack, she was given oxygen through a face mask. The gauge on the 12-liter tank of compressed oxygen read 3,800 millimeters of mercury. You also know 3,800 millimeters of mercury is also 3,800 torr, a direct substitution. Here's the question. How many liters would this same gas occupy at a final pressure of 570 millimeters of mercury if temperature and amount of gas do not change? When it said temperature and gas do not change, we know those variables will not be in the equation. So we ignore temperature, we ignore the amount. So we set up a P1V1 equals P2V2. We rearrange that equation for V2. When we rearrange that equation, we simply plug in the values. It is that straightforward. Be sure that the units are the same. All your pressure units are the same. Then you can work through the problem. So we set it up. We use the equation, 12 liters. We note that the millimeters of mercury will cancel out. And we're left with 80 point liters. Why 80 point? Because 12 liters is our given. Since we have 12 liters as our given, and there are 2 sig figs, we must have 2 sig figs in our final answer. Coincidentally, by the way, all of these have 2 sig figs in them. So we're somewhat cheating a little bit there. But keep in mind, your answer must match the given sig figs. So that's Boyles Law. Boyles Law relates pressure and volume under one set of circumstances to pressure and volume under a second set of circumstances. And in that case, in Boyles Law, T and N are constant, therefore they do not appear in any of the calculations or any of the equations. Let's talk now about Charles's law. Charles's law states that temperature in K of a gas is directly related to the volume when P and N are constant. P and N being constant means pressure and moles will not appear in the equation. So I would simply ignore pressure and moles. And in fact, oftentimes the problems are written where they will tell you the actual pressures and the actual moles, and then they'll tell you they were constant. They did not change. So don't be fooled when you see values for pressure and moles. If they don't change, you ignore them regardless of how many times we write them in a problem, how many times they're mentioned in a problem. Completely ignore pressure and moles in Charles's law. Okay? So, when I think Charles's law, I only care about volume and temperature. I care about the first set of conditions for volume and temperature, and I care about the second set of conditions for volume and temperature. Therefore, if I see a graph involving volume and temperature, I know it's Charles's law regardless of which format it's in. Okay? Whether it gives me a straight line or it's drawn as a curve, if it involves volume and temperature, that's Charles's law. We show you an example of how Charles's law is affected in the diagram where we have T1 at 200 K and V1 at 1 liter. The second set of conditions, change the temperature to 400 K. That means my volume must increase to 2 liters. Okay? So be aware of that. That if temperature goes up, then the volume must go up. So now, let's work a problem using Charles's law. Here's a problem. Helium gas is used to inflate the abdomen during liposurgery. A sample of helium gas has a volume of 5.4 liters and a temperature of 15 degrees C. Note that temperature is in degrees C. Right away, I'm thinking I must convert to K. Automatically, that pops into my mind. What is the final volume in liters of the gas after the temperature has been raised to 42 degrees C at constant pressure and amount of gas? So when I see constant pressure, even if it told me what that pressure was, I don't care. And I see constant amount of gas, even if they told me the amount of gas, I don't care. Because I am using Charles's law and I only care about volume and temperature. And that temperature must be in K. So we set up the equation for Charles's law with V1 over T1 equals V2 over T2. We rearrange the equation by whatever standard math process you are accustomed to doing it, but it must be rearranged, or you'll put all the variables in to show where they are, and you'll work through it again to show proper math conversions. So V2 would then equal to 5.40 liters times the relationship for temperature. We have T2 divided by T1, both converted to K, and we punch it through our calculator, and we get 3 sig figs at 5.91 liters. Not much of a change, but that's the change. Okay? So, temperature factor increases volume. That's the key take-home point. Temperature increases volume for Charles's law. Then there's Galeos Law. Galeos Law states that the pressure of a gas is directly related to its temperature, K, when V and N are constant. V and N are constant, that means it does not show in the equation, regardless if they give me values for it. I ignore it in any calculations involving Galeos Law. Galeos Law involves pressure and temperature. If the pressure increases, then the temperature K also increases. So pressure and temperature are directly proportional in Galeos Law. No change in volume and the number of moles. Therefore, I ignore those variables. Even if the values are listed in the problem, I ignore them. With Galeos Law, I am only concerned about pressure temperature of the first condition, pressure temperature of the second condition. So, I have T1 equals 2000 K and P1 is 1 atmosphere. When I increase the pressure, the temperature goes up. If I increase the temperature, the pressure goes up. That is the relationship of the Galeos law. It is at constant volume and constant amount, moles. If they say grams, you think moles because you know how to convert grams to moles by using a standard dimensional analysis. So, pressure 1, T1, pressure 2, T2, that's the relationship that I consider for Galeos law. So let's work a problem. An oxygen tank has a pressure of 120 atmospheres at a room temperature of 25 degrees C. Right away, I see 25 degrees C. I think K. And I've converted it in my head already, but I'm going to show it on my paper by writing 25 plus 273, just so it's clear. And I show all my work, so I've done that conversion already because that's how I think. If the temperature of the gas inside the oxygen tank reaches 402 degrees C, which I think in K, 402 plus 273. And as a habit, I would suggest if you're doing this on paper that you simply write it right above it, right in the problem. 402 plus 273. It's clear there that you made that conversion. What would be its pressure in atmospheres, ATM, if the volume and the amount of gas do not change. When it says the volume doesn't change and the amount doesn't change, even if the values are in their problem, I ignore them because they are not involved in Galeos law. Okay? So let's read it again. So we have pressure of 1 atm. I mark that directly on my problem. So I see pressure 1. I see T1. I mark that directly on my paper. So I'm starting to see the variables shape up now. I see temperature, which is T2. I mark that. Therefore, the only thing missing from Galeos is P2. So I know that's what I'm calculating. I know what my equation should look like now because I have the 3 variables marked, written, and noted, and I'm only missing 1 variable. So I take my P1 over T1, P2 over T2. I rearrange it by standard math processes. I get the equation for P2 equals P1 times the ratio of T2 over T1 in K. I plug these values in and I obtain 270 atmosphere. I note that my starter material had 2 sig figs because 120 has 2 sig figs. I ignore the 0 on the back side of it, and therefore I write 270 ATM regardless of what my calculator comes up with. I must obey the sig fig rules, and therefore I have 270 ATM. So Galeos law ignores the volume and the amount, the moles, because they are constant in the Galeos law. So in the Galeos law, I'm concerned about the relationship of P1 to T1 to the second set of conditions, the P2 over T2. That brings us to Avogadros Law. Avogadros says that the volume of a gas is directly related to the number of moles of the gas, and that makes sense, doesn't it? That the volume is related to the amount, and the amount is measured in moles. If the number of moles is doubled, the volume must double at constant temperature and pressure. Constant temperature pressure means I ignore those in my calculations, even if the values are mentioned in the problem. I simply ignore them because at constant pressure and constant temperature, I am only concerned with V1 over N1, which is the first volume and mole condition, to V2 over N2, which is the second set of conditions. So essentially, what we're doing in all of these equations is using the combined gas law and ignoring the variables that are constant. So if you understand the math of that, you can simply memorize the one equation for the combined gas law, and you cancel out the ones that are constant. Even if the values are mentioned in the problem, we ignore them. So we have the first set of conditions per second set of conditions. We show you the diagram here. So if we start with 1 mole at 1 liter, if the volume increases, we get 2 moles. If the moles increase, we get 2 liters. That is the relationship. We can actually do this by starting with the final ones and working backward as well. Okay? So we simply do this by noting the variables. And the variables that are constant, we ignore them. We don't use them. So, let's work a problem. A weather balloon with a volume of 44 liters is filled with 2 moles of helium. So I see my volume and I see my moles. So I've noted already with a V1 and an N1. What is the final volume in liters if 3 moles of helium are added to give a total of 5 moles of helium if the pressure and temperature do not change? Pressure and temperature do not change. I ignore them in any calculations that I must do, and I simply mark up the variables in the problem. My final volume is not 3 moles, it's 5 moles for the total volume. Watch for that in the problems, because you look at it, you say, gee, I have 3 different variables for moles. but actually what you're interested in is what's the final. So we add the 2 plus the 3 to get 5 for the final. Watch for that in working problem with Avogadros number. The common mistake is to try to make that 3 become the answer. It's additive. You have the 2 moles plus the 3 moles. You will find later that the pressure and the number of moles of a gas is additive. You simply add them together. Okay? So be aware of that. So you have the 2 moles plus the 3 moles, and you intuitively know this, right? So 3 plus 2 gives us 5. So we take the V1 N1 equals V2 N2. First set of condition is related to the second set of conditions. We rearrange the equation using standard rules of math. And we have an equation that says V2 equals 44 liters times the ratio of the final number of moles divided by the initial moles. And we get 110 liters. And that makes sense because we have 2 sig figs and the number went up. The volume increased. And that's what we would expect from Avogadros Law. So, Avogadros Law involves moles. And we now know that as the volume increases, so do the number of moles. So you want to be aware of that relationship. So with Avogadro, we have the pressure and temperature constant, no change. Therefore, we ignore it in any calculation, even if the values are given in the problem as being coincidental. Okay? So mole factor increases volume. That is a take-home principle for Avogadros number. Now, having gone through this, we can understand now the combined gas law. We have been using the combined gas law throughout each of the other laws. Okay? But we noted that when they're at constant temperature, pressure, volume, moles, or what have you, we only write in our equation the ones that are not at constant. Those that are changing, those that are impacting the system. So now we can take a closer look at the combined gas law that we've already learned to use. We now understand the principles. We understand the direction of change on each of these variables. So let's talk about it. The combined gas law. This law incorporates all the pressure, volume, temperature relationships for gases that we've already studied. You already understand how to use them. You understand how to note each variable as you walk through it. It is useful for studying the effect of changes in 2 of these variables on the third variable. So we change 2 variables and we look at the third variable while the amount remains constant. Since the amount remains constant, that means we do not include it in any calculation, which means that in the combined gas law, we do not see the moles. So the combined gas law is holding the moles constant. And that's important to note. No change in the number of moles for the gas. Therefore, we have the PV over T for the first set of conditions is related to the PV over T for the second set of conditions. All right? Combined gas law ignores the moles because they are held constant. So, let's work a problem using the combined gas law. Here it is. A 25.0 mil bubble is released from a driver's air tank at a pressure of 4.00 atm and a temperature of 11 degrees C. Right away, I see 11 plus 273, which is 284 K. I see that initially because I want to convert to K each time I see these temperatures. What is the volume in milliliters of the bubble when it reaches the ocean surface? where the pressure is 1 atm and the temperature is 18 degrees C or 291 K. I write that directly in my problem so that I see it there. I write 273 at the top of the page or right there above the 8 plus 18 and I get it. So I'm using the combined gas law. Well, we know that the what? Number of moles are constant. Therefore, we set up a relationship of PV over T for the first set of conditions, PV over T for the second set of conditions. I go back in my problem and I note all my variables directly above them so that I can track them. And what I observe is that I'm only missing one variable, and that's V2. I rearrange the equation mathematically for V2 using standard math conversions, and I set that up where V2 equals V1 times the ratio of P1 over P2 times the relationship of T2 over T1. So, I plug in the values for each of these that I noted in my problem, and I run the calcs through, and my answer must be in 3 sig figs, which it is at 102 milliliters. Occasionally, a problem like this, they'll give it to you in milliliters and want it in liters. That happens. Work it through one way first and then make the conversion, or make the conversion in the middle of the problem somewhere. Doesn't matter whether you do it through in 2 steps or one complete long dimensional analysis. I would tend to suggest that you do it in 2 steps. However, I am known for doing them in 1 step. So be aware that I'm comfortable with you doing it in 2 steps or 1 step, as long as you don't violate any rules of math. As you will be learning later in the lecture of Chapter 9, gases aren't always ideal. They're not always well behaved. However, it is convenient for us to treat them as what we call ideal gases, which gives us an indication of the amount of force, pressure, and other properties that might be useful for carrying out gas law chemistry. So let's talk then about this concept of ideal gas law. The equation is PV equals nRT. And you've seen these variables before. You have P, pressure, V, volume, N, moles, and T, temperature, in K. But you now have a fudge factor, or that must be considered. So this is our equation. We show you here ideal gas law constant, R, and we show it to you in 2 different units. So you want to be aware of that the units must match. So you choose your R depending on the units of the problem. When working problem using ideal gas law, the units of each variable must match the units in the R you select. So you want to be aware of that. Now, when we think of this ideal gas law, it is very helpful to know that the conditions of 0 C and 1 atmosphere are called standard temperature and pressure, a concept we have already introduced. This is important because oftentimes knowing that it's at STP can help us get to volume. And in fact, STP is what allowed us to determine the R value. So I want to show you that and re-expose you again to STP. So scientists might use STP to derive the gas law constant. Okay, so be aware of that. And we know that 1 mole of any gas at STP is 22.4 liters. That is important to note. Now, more times than not in Gen Chem, we don't ask you to derive the R. You simply look it up on a table and you plug it in. But be aware that that value R has been experimentally determined at STP, standard temperature and pressure. So let's do a calculation. calculate the pressure in ATM exerted by 1.82 moles of a gas in a steel vessel with a volume of 5.43 liters and 69.5 degrees C. Right away, I convert the 69.5 degrees C by adding 273 to that right away. Note that in some textbook and in some calculations that could happen with some of the online problems that you might do, the value for K is 273.15. So you want to make sure that you are aware of that in this discussions that I'm having, I have chosen to round those off for convenience. Okay? So be aware, some calculation will require you to take it to 2 decimals. So we have 1.82 moles of the gas, we have the volume, we have the temperature, we have the equation, PV equals nRT, because we're going to treat it as an ideal gas, which is a convenient way of treating gases. Because there's no change in the gas properties, we can use the ideal gas equation. Okay? So we rearrange the ideal gas equation and we obtain P equals nRT over V. So we mark off the variables in our problem simply by putting a pencil note above each of them. We see what they are. We check the units to decide which R value we use based upon the units. And in this case, we note that the pressure must be in atmospheres. Therefore, I take an R value that has atmospheres in it. I put in the values, I run the calcs, and I get 9.42 atmospheres because my original given is 1.8 moles, which is 3 sig figs. My final answer has 3 sig figs. Note that in CHEM, being able to give the answer in the proper number of sig figs is very important. It is absolutely important in any lectures that I give. I evaluate all final calculations based upon the rules of sig figs. Let's work another problem. Let's do another example. Calculate the volume in liters occupied by 7.4 grams of ammonia at STP. Right away, as soon as I see STP, I know that's 0 degrees C or 273 K. That's my standard temperature. I know my standard pressure is 1 atm or 760 millimeters of mercury or 760 torr. And I also know, very important, that 1 mole of any gas is 22.4 liters. So right away, I know I have that as a possible conversion factor. As soon as I see SCP, I think 22.4 liters per every 1 mole. All right? So, what is the volume of 1 mole of an ideal gas at STP? How many moles are there in 7.4 grams of ammonia? So we basically have 2 problems. Do not try to work these as one problem. Simply blindly do the first, then blindly do the second. Okay? So let's start then with the first. Recognize that 1 mole of an ideal gas occupies 22.41 liters, or 22.4. That's what it is at STP. And we will use the molar mass of ammonia as a conversion factor, 17.03 grams. Now, you can decide these things up front, or you can right away start to put in the variables and see what's missing and then decide what you need to go back and calculate. So I'm showing you here a little bit different to show you the options you have toward working these problems. I strongly suggest you set up your equation first, start to put in the variables that you do have, and it will automatically tell you what you're missing, and you go back and get them. We also just like to show you a map for doing this. Some people like to see the maps. Again, you can do these the way we've done them already by simply putting in the equations, but I wanted to show you other routes to doing these problems. But in the end, we find that V equals the grams times the conversion to moles, which is 17.03 per 1, times the conversion to liters. And that's what we do. We basically set up a dimensional analysis and punch the numbers through. And we get 9.74 liters. Now recall I said you treat this as two problems. The first problem was simply to recognize the 1 mole equals 22.4 liters. That was your very first problem. So be aware of that. You note that, you write it down, or you do the conversions. But in most Gen Chem classes, you're allowed to simply state it that an STP, by rule, by law, as we do with laws in math, 1 mole equals 22 liters of any gas. So that was your first problem. And your second problem was to simply use that as a conversion factor to get to the 9.74 liters. How about another problem? Dinitrogen oxide, laughing gas, is used by the dentist. What is the pressure in atmospheres if 0.35 moles of laughing gas at 22 degrees C ICK, in my mind, in 5-liter container? So basically, you use the ideal gas equation, you set it up, PV equals nRT, you rearrange it to solve for P, we take the values from the equation, we put them in the equation, we basically plug them in, we run the numbers through, we make sure we're using a value for R that has the proper units, and we obtain 1.70 atmospheres, 3 sig figs, because we start with 3 sig figs in R given. So that's how we use the equation. We use it simply by noting the variables, plugging them in, working it through, using K, and using an R value that matches the units required. We can also use the ideal gas law and the mole relationship within the ideal gas law to determine the molar mass of a particular compound. So let's do that in this example. What is the molar mass in grams per mole of a gas if 3.16 gram of gas at 0.750 atmosphere and 75 C, which I convert automatically to K, occupies a volume of 2.05 liters? It's asking for the molar mass. Therefore, I think moles, because it said molar mass. So if I get the moles, then I can work through to get to molar mass. So I rearrange my equation, ideal gas law, to solve for N. I take N, I choose R to match the variables in the problem. I take those, I put them in the equation as we show you here. You've seen this before, we're repeating it. We make sure we convert to K, we punch the numbers through, and we make sure that we report the proper number of sig figs, and I have the moles. So that's step one in working this problem, and I treat it as two different problems. I get to the moles, and then I can take it from there. Okay? So now I've gotten to the moles, right? Well, what do we know for molar mass? We know that molar mass equals grams per mole. Okay? So, since we have the grams given at 3.16 grams, and we have the moles that we have calculated, we can do our molar mass, would be the mass in grams divided by the moles. And we basically put those numbers in, we run the numbers, and we get a 53.7 gram per mole value. 3 sig figs we started with, 3 sig figs in our molar mass. At this point, students may have developed a habit of looking on a periodic table and either using one that always uses 2 decimal places for molar mass or 3 decimal places for molar mass. When you carry out calculations, you always want to make sure your answers are based upon sig figs. And certainly if it's a lecture of mine, I will look for significant figures for the final answer. We can also use these equations to determine volume based upon a chemical reaction. So let's work a problem. How many liters of carbon dioxide are produced at 752 millimeters of mercury? Not quite 1 atmosphere, because we know 760 is 1 atmosphere, so this is slightly less than an atmosphere, at 24 C, which is slightly below our standard room temp. So we would add the 24 to 273 for a 25.0 gram sample of limestone, which is calcium carbonate. So we take a look at the balanced equation that we see. It looks balanced. If it were not, I would balance it. Anytime you're given equations in Gen Chem, be sure you check that they're balanced before you start to do the work. That is critical. Oftentimes, the professor will not remind you of this as the year goes when you're taking Gen Chem, but it's very important that when you see an equation, you check to see that it's balanced. If it's not, balance it first. So we take the 25 grams after we balance the equation. We do a times bar with grams on the bottom because that is the way we do dimensional analysis. The gram is converted to mole on the top. We do another cross bar with moles on the bottom of calcium carbonate. We write the identity of each species as we go through this process so that we don't lose track of what we're doing. So we have 1 mole of calcium carbonate to 1 mole of carbon dioxide. That relationship comes from the balanced equation. There's 1 mole of carbon dioxide for every 1 mole of calcium carbonate. We calculate the numbers through. Our calculator gives us one answer. We take that answer and we convert it to the proper number of sig figs, which in this case is 0.250 moles of carbon dioxide. So now we have the gas, moles. That's how many moles. We did that because we are looking for liters. As soon as we see liters and we treat it as an ideal gas, we are really after moles because we can take the moles and we can get to liters through the ideal gas equation. And that's the thought process you have to get used to. And that's why I want to work through more of these problems. When we see liters, we think ideal gas law. Ideal gas law says I need to get the moles before I can get there in many cases. So now that we have the moles, we rearrange the equation. V equals nRT over P. We choose an R value constant that has the proper units that we need to match our equation. We know which units to use because we look at the units in the problem, and that tells us which are to be used. We set it up, put the numbers in, we punch one value on our calculator, and that value in the calculator is then rounded to the proper number of sig figs based upon the given 3 sig figs, the given 3 sig figs in the end. And that leaves us with 6.15 liters of carbon dioxide. And that's how we use the ideal gas law to calculate pressure, volume, temperature, moles. So again, we can use the ideal gas equation to calculate pressure. We can use it to calculate volume. We can use it to calculate temperature. We can use it to calculate moles. We can find the R value as well, but oftentimes in Gen Chem, we don't exactly ask you to calculate R. We expect you to be able to look at a table and choose an R based upon the problem at hand. The variables within the problem at hand will tell you which R value to choose. Your R value must match those values in the equation. So there you have it. Lecture 1, Chapter 9, Gases. Lecture 1, Chapter 9, Gases.